All right, welcome to today's webinar. We will be starting in a few minutes. We're just going to let people join. If you have any questions during the webinar, please feel free to type your questions in the chat and I'll go over it in a few minutes. We're going to start in about 2 minutes. Okay, I think we are good to get started. Welcome to today's webinar. Today's webinar will be on a multi-vendor DC microgrid design. Some housekeeping notes. If you have any questions during the webinar, please feel free to type them in a chat and we will go over them during the last 10 minutes or so of the webinar, and they're going to be addressed in the order that they came in. A link to the recording of this webinar will be available to all the registrants following the program at RE+ events. So let's go ahead and get started. This is the design webinar series number 2. And today what we're going to do is we're going to design a multi-vendor DC microgrid. And we're going to go through all the considerations that you have to take into account on a very high level when you're attempting to design a multi-vendor microgrid. So I really look forward to this one. Today's webinar is hosted by Direct Energy Partners. I would like to introduce Direct Energy Partners as a company. As a company, we aim to accelerate the adoption of renewable energy microgrids. This has been our mission from day one, and it's in the company's DNA at this point. I'm the co-founder and CEO of Direct Energy Partners. My background is in electrical engineering, and I started Direct Energy Partners to make sure that the DC microgrids get to fulfill their potential that they promise to the world. Giel, I would like to introduce yourself.
Yeah, thanks. Hello, everyone. Good afternoon. My name is Giel van der Broeck, as you see on the screen. I also have a background in electrical engineering, power electronics, and specifically DC microgrids for about 10 years now. I did first the PhD on the subject before partnering up with Dusan and actually joining the mission to accelerate the adoption of renewable energy microgrids. We're both very passionate about the subject overall, and we're especially passionate about how we can get more microgrids out there, how we can get more microgrids deployed faster together with people. And that's what we're going to share more about in this webinar. So looking forward to it.
Perfect. Well, thanks, Giel. So before we dive into how to design microgrids, I would like to introduce what is the problem that we are facing. The first problem, I would say, is that the microgrid design lifecycle is extremely complex. There are several steps when you're attempting to design your microgrid. There's about 8 or 9 of them. First, you have to define your project goals. You have to evaluate your project benefits, and you have to figure out where this microgrid is going to go. Steps 1 to 3 is really what we call the concept phase of the microgrid. This is where everything starts. Once you're past your concept phase and you're comfortable with your techno-economic analysis, you get into your design phase. The design phase is where the systems engineer takes place. This is where you create your construction sets, your permit sets effectively. This is where you make sure that every wire lines up with the system and it performs to a certain tier of operation. Once you get your designs done and you get them permitted, you typically go to a procurement phase. Procurement phase is central. This process can be long, So it's very important to be on top of procurement. And after the equipment gets procured, it goes into the implementation phase. And once the system gets installed, it goes into the commissioning phase. This commissioning phase is extremely important. This is effectively where you get the microgrid set up and start each system individually and make sure that they work according to their specifications. And then you also test the system as a whole, run it through its paces before you hand them off. So make sure it works in all worst case scenarios as it was intended to design. And once that happens, you can hand over the keys to somebody for operation and maintenance. And if you're really, really lucky, you get to upgrade or expand or retrofit your microgrid. And I say lucky because this process presently, just steps 1 through 8, can take years, just due to the complexity that it takes to coordinate all these steps. So this is what the industry is used to presently, but we think there is an extra step before number 1 that takes place. And I'm going to let Giel take it from here.
Yes, true. Because we all, I mean, experience this type of life cycle when running projects, but we are also very much aware that this process is never a step-by-step process. It's a continuous going back and forth. And typically where it starts, it's somebody having an idea, somebody thinking about, I have a particular facility. Let's say I have an EV charging system that I want to deploy at my parking lot. I have some solar, I have some battery storage. I experienced power quality issues or disturbances in the past. That's typically where a project starts, in the mind of somebody. And that somebody then gathers people together, and that's where the idea starts. That's what we call the ideation phase of a project. It's the phase where the current situation gets clarified. It's the phase where ideas get generated. It's the phase where actually the complete brainstorm and the initial layout and concept of the system gets developed. And that's where we believe that there's currently a gap in terms of tools and know-how to structure and organize that process today. It's like, where do these ideas go? I mean, today they end up in PowerPoint slides. It starts probably at the whiteboard or a hand sketch note. We all know how the process goes today. Okay, but what happens next? That same sketch evolves, matures. You get eventually to a bill of materials, but all the information somehow needs to get centralized and organized in a single place. And currently, what tools do you have to do that? Very few, and that results in a very fragmented and chaotic design process, especially in these early stages of a project.
Yeah, we've all experienced it, right? You get together in a room and you say, I want to build this microgrid. And we talk about it for an hour, and then you send somebody away to drop that single line. A week or 2 will pass by, and that person comes back and captured half of your thoughts and doesn't have a standard design, and any kind of subsequent revisions typically take several weeks afterwards. So we believe it's extremely important to capture some productivity at this ideation phase. And so today, when we are designing with the microgrid, we're gonna show you the tool that we're doing that will allow you to draw these systems at the speed of thought. We believe we need to capture every thought and be able to configure it live effectively. So let's summarize this quickly. The reason that it takes several years to design a microgrid is, yes, there are huge knowledge gaps in industry, but the life cycle is extremely complex, right? There's a lack of ideation tools where you can collaboratively design microgrids. Products are homeless. I skipped through this in the procurement stage. But even finding products for microgrids today that you can actually make designs with is extremely difficult. If you design something that doesn't have a product attached to it, it's just a white elephant drawing. Ideas are nice, but the products must exist in order to be able to deploy them and execute on them. There's lack of harmonization. What does this mean, Giel? What is lack of harmonization?
Well, I think the best we can get that message across is by like sharing an example. So, I mean,
Okay.
at a certain point, let's say you're building a renewable energy microgrid. I mean, in our case, mainly DC microgrids, and you're there and you need an EV charger, DC input EV charger. Where do you go and look in the first place? That's where the homeless products come in. But then the second thing is like, I now found like 3, 4, 5 suitable products in there, quote unquote suitable. How are you going to assess that at the end of the day, whether that product is suitable for your system? You're going to end up having a variety of data sheets, product catalogs, application manuals that you get from the manufacturer sent to you. But how can you compare one EV charger against another in there? One will list the efficiency in one way, the other one will list the efficiency in a different way. One EV charger will have a circuit breaker already integrated, another one won't have it. One will support certain communication protocols, another one doesn't. But all these type of attributes and specifications are extremely important to make a decision at the end of the day. So, and that all starts with calling the same things the same way. So that's what we mean by harmonization.
That's right. That's right. You touched on a few points. Information is fragmented, it's all over the place, and it's not standardized. And so today we'll show you, what we can do as an industry to harmonize that information. And problem number 6 is just lack of collaboration. Yes, there's big knowledge gaps, but I think the entire industry needs to collaborate more. So today, we are going to show you how to design a DC microgrid with a product that DEP introduced to the market called DCIDE. And DCIDE is made to design microgrids faster together. DCIDE has an intuitive design interface. This was extremely important for us to make sure that you can drag and drop features. So you can really move at the speed of thought, so you can really focus on the application at hand. It has real-time collaboration built into it, and you'll see that today because 2, 3, or more people can design a microgrid faster and ideate together. And we are extremely proud to introduce the AI-enabled product catalog. This knowledge gap, we believe, can be filled in through a AI-enabled product catalog that searches the actual information that the product has. So instead of talking about it, I would like to kick off a design. Giel, are you up for it?
Yes, let's do this.
All right. I'm just gonna switch the screens here quickly. And we can get started. What's the first step to designing a microgrid, Giel? What do you have to do?
The first step typically is actually listing what actually you're about to get built in there. Like, what's the list of assets? Like, what are the loads that you need to power? Are there certain lights? EV charging we already mentioned. Are there certain type of critical loads? So basically inventorize all the assets that require power. I mean, that will dictate your requirements at the end of the day.
Right. So solar storage, EV charging, like look at your high level generation sources like utility connection, and other loads that can be added. I would say the other things that, when you're like thinking about your microgrid, you also want to like think about like your theory of operation. What is it that you want this microgrid to do? Because it will impact your equipment selection. So typically you want to make sure that these systems work in a grid connected mode, or in an islanded mode. And I would also say that they have the capability to black start. What is black start for you, Giel? What does it mean when somebody says black start?
So indeed, we use the terminology black start to basically characterize a microgrid that can start up from solar generation only. So actually, if you are to start up from solar generation only, your microgrid, it means that also all your auxiliary power needs to be provided from that solar generation. It's very easy to say, like, I have solar generation available. I mean, there's a potential of like 50 to 100 kW of solar, but that doesn't mean that you will be able to energize your entire system, because all the power converters that get in between, all the controls need to get power first before you can ramp up and energize the rest of the system. So if it's a requirement to have black start capability, it means that you need to add additional components in between. That will make sure that your controls and auxiliaries get the right amount of power supply to energize the rest of the system. So
That's right. That's often overlooked. It's maybe we can have a separate webinar for that. It's often overlooked, but it's also one of those critical things. If you have on-site renewable energy, you should make sure that it can start off of that like solar instead of requiring the utility. So Giel, I see you jumped in here. Why don't we put together like this skeleton of the microgrid that we kind of listed here?
yeah, let me do the EV charging.
So you can add some EV charging, we can add some solar, and we add some power conversion equipment, and we can add a distribution panel. Now, this is actually important. You know, as you're designing your microgrid, you should be thinking about how are these microgrids going to connect in the real world. So in DCIDE, you know, you can't actually connect two lines in empty space, because in the real world, there's a physical equipment that's going to be there, whether it's a junction box or a distribution box, if you will. All right, so you've set up your problem statement. You kind of went from the list, and we put up all the our components, and so typically just, you know, the second phase will be to connect these components together, and this is how the ideation phase starts effectively. Now, when we connect components together in DCIDE, you notice that the colors change or are automatically assigned. So red indicates AC power, blue indicates DC power, and there's power for directionality set. Because there's no components presently attached to these designs, the power flow direction chooses the most flexible option. Converters can be bidirectional on all the 3 ports. And solar panels typically, well, they only generate power. You do not want to feed power back to them. All right. So what's the next step once you have, let's say, like a skeleton of your high-level components? What would you do next?
So as a next step is like zooming in on the power conversion devices that goes in between, actually. Because in this system, what we're looking at currently is we're connected to the grid. Then we go to a central power converter, which has an AC port connected to the utility, which has a second DC port, which is currently used to charge and discharge the battery. And we have a third port that actually is your DC bus that's distributed by means of the panel. So that means that all the blue lines here from the converter output to the solar to the EV chargers will see the same voltage at their inputs. So, and this also means that this solar system is connected to the DC bus, which is something that we want to avoid, because we want to have maximum power point tracking at the solar side. So that's where we want to introduce a converter. So
I dragged one in
perfect.
faster than you.
Yeah, indeed, that's also something that we want to highlight. I mean, when you're thinking, when you're brainstorming on such an architecture, you want to compare different options. You're generating different ideas, and you want to draw at the speed of thought. You don't want to be interrupted in your flow by the software, which requires you to like rearrange boxes, redraw lines. That line doesn't connect to that line. The lines become like chaotic. So in the ideation phase, what we experienced and what most people also tell us is this tool really enables me to think freely and not worry about how do I get my graphics nice and clean. It takes care of that for you. I mean, like if, for instance, you can move that EV charger maybe to some like to the right-hand side of the panel
That's right.
like that, and you see like these lines automatically rearrange, and that's important because we don't want to block you in that ideation flow. You're thinking about an electrical architecture, and the software should help you to get your ideas across.
That's right. I think that's typically one of the most frustrating parts. And we don't want to become line engineers. We want to add value and be application engineers out there. So this auto reconfiguration of lines, it's a huge benefit, and also demarcation and annotation of where you can where is the equipment actually located. So here we talked about adding a DC-DC converter here. Now, when we are actually trying to figure out if this converter can work with that converter, what are some of the considerations to take? I mean, let's talk about like maybe the top three. How do you go through your selection process today?
Mhm. So the first thing, obviously, is the voltage level. Like the voltage at this port will be the voltage at this port, as we already explained. So obviously, the ranges should match. And in a DC system, in a DC microgrid, you have some freedom there to select the suitable voltage level. 350 volts, 700 volt. That's where international standards are going today. But you can still freely decide, depending on the power level, what voltage is the most suitable. So in this case, if we, for instance, were to select the 700 volt DC microgrid architecture, and we put that as a design decision down, that means that our EV chargers need to support 700 volt, that our lighting system needs to support 700 volt, our inverters need to support 700 volt. And we can also capture that information readily on the diagram. And based upon that, we can actually start already making a first selection of products based upon the voltage level. Now, before we do that, before we jump to the actual product selection, there are more considerations, obviously. Like if I want to select a converter for solar, that means that that converter needs to support solar at the input, and that at the output, actually, it should maintain maximum power point tracking on the solar side. If we are to select the central power converter, that power converter will be responsible for maintaining a stable DC bus voltage. So that 700 volt needs to be maintained somehow. That's the responsibility of that central AC-DC converter. So it's a requirement that at the second port of this converter, where my pointer is at, that that converter supports constant voltage control mode in there. And then obviously a third aspect is also the power flow direction of these components, unidirectional, bidirectional. In this case, the arrows indicate that we want to be able to send power from our DC backbone to batteries, send it back to the grid. So we want to select a converter that supports bidirectional power flow. That's what I would say.
So here, that's definitely, true what you said, and I annotated the diagram as you were talking. One thing I want to point out with the voltages, because that's really the first thing you start looking at. What are the voltage ranges for the compatibility? And we have chosen to support the current OS standard out there for these voltages, because it's also important to make sure that we as an industry start standardizing and to make sure there's more compatible products effectively out there. And so in DCIDE, you can effectively just click the voltages and effectively set them. And this provides a really good visual representation of what your system is starting to look like. The second thing, just to summarize what you said, you look at, current compatibility, you look at power compatibility. We talked about power flow directions. And I would also say that when you're taking two converters that are like foreign to each other, the other thing to make sure we do is controls compatibility, right? So from it's one thing to make sure that they will electrically connect. It's a second thing to make sure, are they going to actually work when we power them on? And so controls compatibility, I would say that's important to look at. And what I mean by that is, yeah, simple stuff, right? Can you control these converters between power mode, voltage control mode, or current control mode? Those are like the three most typical ones. And I guess why is that important here? Like on a very simple level.
So indeed, to continue basically the story of voltage control, let me just give a very basic example. Let's say your central grid connected power converter controls the DC bus voltage in the system. If I now were to connect, let me just drag in a battery to make the case, that battery actually dictates the voltage. It's a voltage source in nature. So actually this battery would dictate the voltage and this converter would dictate the voltage. So the two would start conflicting. And actually the same could happen if I replace that battery by a converter which ties a certain asset to the grid. Let's say I'm gonna use this converter with a battery as a backup source to keep my DC voltage up. If these two converters would operate in constant voltage mode, so the central one and this battery one, they will start fighting each other in there. So one will try to bring the voltage a little bit up, the other one will try to bring it further down, and eventually they settle somewhere where one of the converters will operate in the limits, or the system will basically become unstable and it will just cease to operate. So it's fundamentally important from the reliability aspects of this system that the control modes of these converters are coordinated in there.
That's right. That's right. So when we look at like converter one, converter two, we'll make sure electrically it works, and do they have the control modes? Because once those two things are in place, then with a microgrid controller, you can kind of make sure that you can orchestrate at least their operation. Now, there's a lot more things that go into like, dynamic and steady state stability, but on a high level, when you're like trying to find your equipment, like those are like, you start filtering down and narrowing down before you get into the weeds. And I would say that's kind of like the theme of the design we want to emphasize, is that before you get into the weeds, start with the high level stuff, right? Start with the big items and start filtering down before you invest precious time into that systems engineering. that has to do the evaluation of dynamic and steady state stability. You want to have like your top 3 components selected. You want to be somewhat confident that gets selected. So we talked about voltage control, current control, and power control mode. Now I would say, well, why don't we try and find some products? So there's a world before DCIDE, and then there is the world with DCIDE, right? The world before DCIDE, you have to go to trade show, you have to find somebody on LinkedIn, you have to find a rep, send some emails out, go on LinkedIn and say, do you have this product? And just send a ton of emails out, and hopefully people understand what is it that you're talking about. How do we do this in DCIDE, Giel?
Well, in this side, we made that way more discoverable. So actually what you can do is you can, for instance, take that central converter, you can highlight it, and then we introduced that search icon in the toolbar of that component. And this gives you access to our product catalog. It brings relevant parts that have an AC, a DC, and a third DC ports. It brings them at your fingertips. And as you see on the right-hand side, so you get a number of search results. You see the specifications of these components, the main ones that you're looking for, like the voltage and the power on all 3 ports of this power converter. You see the manufacturer, you see an image of the product, the manufacturer logo as well. And then it becomes as easy as clicking a button to link this component to your design. And as you do that, actually, you notice that all the specifications of this component will be stored with your design. So power and voltage, as we already displayed, but also, for instance, the isolation of this converter. So this converter is isolated on the AC side from the DC side. That's represented by the double line in the diagram. So actually your symbols immediately adopt the characteristics of these components in there. And that's very important to address the problem of fragmented information in there that we had in the slides, because now you can basically make a decision whether this component fits your design. Did I want an isolated converter, or don't I want an isolated converter? You immediately see that and have that information available while you're designing, while staying within the design in there.
And I would say, like, isolation is important, just kind of like a side comment. If you're doing like a retrofit design with solar, an isolated converter is most definitely one of the safest way to go, because it isolates the different grounding on a solar side and on your planned DC side. And prior to DCID, you'd have to like redraw these things, but here we can just click isolation and the symbols update dynamically. So the double lines with the gaps, they actually mean something. I would say, grounding, that's also like a separate topic on its own, but I would say rule of thumb, isolate, and that should be very flexible when you're putting these systems together. So we found this product, but like we're not quite sure what is it that you can do with it. So if you want to understand what more can you do with this product, or what are its capabilities, on the right hand side, I kind of clicked on the data sheet, and you can get into a more detailed data sheet. That's actually what he was talking about earlier, a harmonized data sheet. So what, Giel, maybe you can just point out a couple of things that are important in this harmonized data sheet.
Yeah, so in this harmonized data sheet, we want to go beyond what you currently find in data sheets. I mean, the harmonized is key here because we spend a lot of time and effort also together with Emerge Alliance, to actually come up with data models for this equipment, with data models that work for every type of power converter, for every type of battery, and harmonize and standardize on the terminology that we use. And we subdivide this into like sections. So we're talking about electrical characteristics, for instance, which are the most important in our design process. So we have voltage, current, power, frequency, which are like the usual suspects that you typically find in data sheets. Some things that are sometimes already harder to find is like, does this unit support like bidirectional power flow? Is this actually bidirectional? Is this isolated, yes or no? Frequently, power supplies do not list that information in their data sheet. You somehow have to derive it, or there's some icons or symbol referring to it, but it's not clearly displayed at all times. Definitely not like things like capacitance, which on the DC side are important to take into account. How much capacitance will I have on my DC bus is a design parameter I should know. So I got to add up all the power conversion units that are attached to my system. And then the built-in features, like does it have certain protection features? In this case, port 2, for instance, features residual current detection built in to this unit. Port 1 has voltage, current, and power measurements. So those are measurements you then can retrieve in your controller and use them to display it or for other purposes.
And I would say, I would say these control methods we talked about, does the converter have the control methods? And like, just to find out, presently if a converter has these control methods or the paralleling capacity or built-in features, that's a monumental job today. This is why microgrids are complicated to design. It's one thing understanding what to do with information once you have it, but it's also like gathering that information. So a data sheet is not just a data sheet. And so with these interoperability data models that we are working on with Emerge, which is powering this data sheet, our mission is to make sure that we standardize the terminology and we introduce compatibility attributes that are actually required to make decisions. So when I need to figure out if a converter works in my system, there are certain things that I need every single time. And if I look at one converter and a second one, the data sheet should look the same. And we should not spend weeks trying to figure out which person in which department, has that knowledge and information that we need. So this is one way we're trying to reduce I guess, make the industry more productive. So the Emerge Alliance is working on this open interoperable data models, and with DP, we're trying to make sure this data is readily accessible at your fingertips as you're designing. Another way we're trying to make sure that we close the knowledge gap is by the introduction of AI. So with these product catalogs, we have tied in an AI engine that looks at all the information, and this is important, all the information that is released with that particular product that you as a designer can interrogate. And some, as you're making your design decisions in this other tab, I mean, this is just a single line diagram. My first question typically would be, something like, does this unit require external overcurrent protection? And typically you would have to, again, just, read through various manuals, but we put it at your fingertips and the AI can help you and answer and says, yes, okay, this unit requires a 50 amp 3-phase, 3-wire AC breaker on the AC side. And on the DC side, it's 1,000-volt DC 100 amp fuse breaker. Great. That is extremely useful. And if you want to verify where it's coming from, you can click these reference numbers and it actually pulls up the data sheet, where this information is coming from. However, as a designer, you can now go back and effectively, dragging these circuit breakers to your single lines because they are needed. Oftentimes you assume it comes with equipment, but well, in this case, it's not. And you can set your nominal currents, I guess this was 100 amp one, right? Just so you can come back to this later and not lose it, if you will. So information staying in the same place. Go ahead.
Yeah, and I mean something important to stress here as well, like as you see this design, actually it's evolving. Like in reality, before we used DCIDE as our tool to generate ideas on microgrids, this diagram would have been redrawn already 4 or 5 times. It starts with just something on a sheet of paper or a whiteboard. Somebody takes a picture of that. It gets sent over WhatsApp or by email to somebody else. That somebody else then converts it into a PowerPoint slide. Then somebody else comes in and starts adding more equipment like, okay, we need protection devices, we need controls. And every time and time again, you redraw the same system as what you started with. What we want to bring to DCIDE is a place where all this information gets organized and where your ideas can grow as well as your insights develop in there. So
exactly.
remain on the same page, literally, throughout the entire design process.
Exactly. I fat fingered something here, so we're gonna have to go back to to the design.
Okay.
All right, so we're here back at the design, and to your point, you can go and interrogate the AI, and this is kind of like a foreign concept. You can really ask it, anything. I mean, you can ask it things like, explain how to support unbalanced loads. Now, most people typically wouldn't think about this, if you will, but when I say unbalanced loads, it's really mostly on the AC side that I'm referring to that. And so like you said, this diagram is evolving, and the support of unbalanced loads is really important, I would say, during the an islanded phase, not necessarily a grid connected phase. So what I would typically do is, move that grid and add a transfer switch. Transfer switch helps you isolate between the utility and the rest of the system. And then typically we would add some kind of a panel that now you have like an effectively an AC panel that you're connecting your load to. And, you can add an arbitrary AC load that you can define and change this to an AC load. So this question about unbalanced loads really matters when you're disconnecting. And what did the AI say while I drew that in order to save time? Yep, you need 3-phase, 3-legs loads, and you can find it in the application note on how to support that. Now that's the with the 3-phase power that you have here, you would typically run it at I would say 480 volts AC, and because that's what the converter actually ends up supporting. But if you need to do unbalanced loads, what you would need to do is add a transformer to your design. So, and the transformer, it can be a few different designs, I would say. One could be a delta Y transformer or a zigzag transformer. So I would, if I'm collaborating with Giel, I would just tell him, let's evaluate if a delta Y transformer is best for this design or a zigzag transformer. Now, there's trade-offs between that too. You have to really start looking at the inductance and how much your system can handle, and that's where some of those additional metrics in a data sheet will become handy. But Giel, I see you dropped the message here. Any thoughts on this particular design? There's several thoughts that I have. So this is a DC circuit breaker. We're drawing a single line diagram over here. However, when it comes to like DC selection, before you even start getting into the fault current capabilities, I would say it's important to look at the voltage capabilities of the circuit breaker. So here, let's go ahead and find a circuit breaker that could work for this system. And so when you click the search icon, we filter down immediately what could work that effectively works with this power converter and the voltages. And we can look at that, we can link it, and we can look at that data sheet in more detail. So just like we looked at a power converter data sheet, this is harmonized data sheet for circuit breakers. But I would say, the most important attributes to start with are looking at the poles and the voltages per pole and the maximum voltage. Why is that, Giel?
Yeah, so when you're selecting circuit breakers, which is kind of a science of its own, you indeed gotta start with the voltage of the circuit breakers. I mean, typically these DC circuit breakers, they have like multiple poles that are connected in series. Why do you have multiple poles connected in series? Because as soon as you start interrupting the current, actually an arc will emerge. So that arc needs to be interrupted by actually making sure that there's enough distance between the two contacts as they're separating. Once they're separated and there's enough distance in between the poles in there, that arc will extinguish at the end of the day. So that's why you have these poles in there, and that's why these circuit breakers are typically rated at, for instance, this one at 250 volt per pole. So this means that if you were to interrupt a 1000 volt DC, or in our case, a 700 volt DC, like 3 poles would be sufficient in this case.
Yeah, exactly. So those voltages and poles, I think they are important to start with before you get into the weeds on the fault current capabilities. We have limited time, so we have about 12 minutes left. I would say, one other thing to mention on figuring out the fault current, we added one circuit breaker here, but when you're designing your microgrid, you have to figure out where is the fault current coming from. In your typical AC system, the fault current comes from this utility out here. And for all intents and purposes, that fault current, when something shorts to ground, is unlimited. So there's huge fault currents. But if you look at this DC microgrid design that we put here together, fault current sources, even though there's a battery attached here, go through a power conversion unit. And even though there is solar here, they go through another power conversion unit. So what that means is that your fault currents are limited here. And so you really want to make sure that when you select your electromechanical circuit breakers or solid state breakers, that you have actually enough fault current capacity to trip them as well once you filter them down, once you're trying to make your selection. We have some questions in the chat here, and I would like to make sure that we answer that. So first question for you is, what are the benefits of a DC system for EVC or a building?
Mhm. Maybe do some, before we answer that question, maybe one more thing to show is how to share a diagram. And maybe we can
Good point.
just share the link with the audience in here. Then everybody can actually join and view this diagram as
That's
well.
true. So so if you do want to share this design with people, you can click invite to collaborate. Private means, yeah, you can invite one-on-one, or if you want to share it with everybody, you click that button and click copy to share. And I think I should be able to drop this into the Zoom chat. And I think it's hard to find a Zoom chat then.
And that's at the same time a very important feature too. I mean, since we have this feature, actually, we share links with one another. Like we jump on a call, somebody brings up a diagram, generates a link, the other one jump in and actually start designing together. But also as the project evolves, it's like you can always get back to that same design, watch the comments, watch the conversations. So it also helps you to work asynchronously. You no longer have to wait for that next microgrid design review meeting to move the design process forward. I mean, couple minutes a day and you can make really steps, way more progress in this a shorter period of time. So
That's
but back
right.
to the question, quick intermezzo. So what are the benefits of a DC system for EV charging or a building? We only have 8 minutes, right? I I mean, if I'm asked about what are the benefits of a DC system, it ultimately all boils down to compatibility. I mean, we're talking about integrating solar, storage, EV charging, lighting, all behind the meter. And the way we do that today is we put a inverter in between and we connect it to the AC side. Although all these loads and generation sources and storage actually physically operate and run at DC power. That's why you need those electronics, these power converters in between to make them work with the alternating current grid that we receive from the utility in there. And actually, by switching over from an AC infrastructure to a DC infrastructure, you can greatly save on these power conversion steps that go in between. Like you still will have some power electronics, but if you go under the hood, it will be the minimal set of electrical components that you have in between. So less components, it will be overall smaller. It will be more efficient because you will have less components where current is flowing through. It will be more reliable because you have less components in the path that may fail. That's an argument, for instance, to use these type of architectures in data centers. But ultimately, it all boils down from the compatibility argument. It are DC sources, DC loads, DC storage, so it makes just the most sense to interconnect them at the DC level. And then the second advantage, that's in my top three of DC system advantages, is that you can transfer more power across the same type of cable infrastructure. So you save on copper wiring or aluminum wiring in between. And that can be significant, like in industrial DC projects, for instance, there are reports saying that you can save about 40% in the overall copper of your installation. So smaller cabling, more cost savings, and also less losses along the way. And then the third argument for DC microgrids is they are inherently controllable. Like the system that we have put together here, which by the way is something that we did in somewhat over half an hour. Imagine doing that in a PowerPoint slide. The system that we put together, I mean, if the grid fails, in this case, like your DC side will remain operational. I mean, all the electronics will continue to function. and you don't need like complex transfer logic and transfer switch gear to switch from grid connected to islanding mode. Everything connected on the DC side will receive power and will even not experience that grid outage in there. If you want to achieve the same level of reliability in an AC microgrid, you will end up having quick transfer switch gear in between, and that does exist, but because of these requirements, it will end up being pretty expensive as well. And then as soon as you want to reconnect back to the utility, then you got to synchronize, match the phases, etc. So that process also adds more controls, more complexity, and ultimately adds to the cost of the entire system.
Thanks, Giel. Thanks for that. While you were answering that question, we were trying to figure out how to share the link over Zoom, and looks like we'll have to send it out afterwards. So we'll follow up with the audience. It's a Zoom thing. I think we have to get better at using Zoom. Now we have only a few minutes left, so I have some housekeeping items that I would like to go over at this point, since we covered the questions. So I'll get back into the presentation slides quickly. Okay. So I would like to remind all the attendees that there are several webinars series happening. Some of the upcoming ones are the Electric Avenue series. They're on May 22nd and June 18th. And further deep dive into microgrid design series with Giel and I are happening on May 29th and June 12th. Those are going to be with other manufacturers as well. So we look forward to seeing you on that webinar. I would like to remind everybody that the eMerge Alliance is on the road. eMerge Alliance is going to be seen at RE Plus in Texas on May 14th and 15th in Houston, and then on July 18th and 19th in Philadelphia at RE Plus Mid-Atlantic. And everybody is going to be at RE Plus Anaheim on September 9th through 12th, so we hope to see you there. And finally, to become a member of the eMerge, where you can help us develop and impact the development of the interoperable data models, just scan this code. Feel free to reach out to me directly or go to emergealliance.org/join. And with that, I would like to thank everyone for attending, and we hope to see you at the next webinar.